The topics of discussion today are the following six. Firstly, I will be focusing on the basic principles of frequency modulation. Then there will be some discussion on the frequency shift keying, which will be followed by articles on principles of phase modulation, phase shift keying, and lastly, I will conclude my lecture with discussion on the following two topics, which are the relationship between modulating and carrier deviation and converting phase modulation to frequency modulation. So, what is frequency modulation? A carrier wave which is of high frequency is an input at one input terminal of the modulator and the information signal to the other input terminal of the same modulator. And at the output of the frequency modulator will be a carrier signal which will be varying its frequency with reference to the information sine wave signal. So the carrier amplitude remains constant when there is no information signal, and whenever a modulating signal is applied to the modulator, the carrier signal frequency shifts proportionately with reference to that information signal. As the information signal, which is the modulating signal, increases its amplitude, the carrier frequency increases with reference to that signal. And when there is no information signal which is applied at the input of the modulator, then the carrier signal will be at its normal frequency, which is set as resting frequency. Now let's suppose we can have a discussion on a frequency deviation terminology. This is the amount of change in the carrier frequency produced by the modulating signal. So if we are having a modulating signal which is applied at the input of the modulator, and let's suppose it is at its minimum amplitude, and when that amplitude changes from minimum to maximum amplitude, then the frequency of the carrier changes from minimum frequency to maximum frequency in that aspect of time, and the difference between the maximum and the minimum frequency will result as the frequency deviation. Another terminology, frequency deviation rate, is the number of times the carrier frequency deviates above and below its resting frequency, which is the central frequency. So the frequency of the modulating signal determines the frequency deviation rate. As the frequency of the modulating signal is increased, the number of times the carrier deviates above and below its central frequency increases, and the frequency deviation rate resultantly increases. Here we have a diagrammatic description of the frequency modulation. We can see over here, this is the information modulating signal, and this is the high frequency carrier signal. We can see over here that these two signals are being applied at the input of the modulator, and on the output of the frequency modulator we have this kind of signal. If you can see, as the amplitude of the signal which is the information signal, increases, the frequency of the modulated signal increases. And when that amplitude decreases, and again from its 0 point starts decreasing to the negative trough, here you can see the frequency of the modulated signal is minimum, and it is minimum at this point and maximum at this point. Another thing you can also originate from this diagram is that when the modulating signal is not applied, it is that time the carrier will be remaining at its normal resting frequency and doesn't change its frequency. This below signal is a diagrammatic representation of a phase modulated signal, which will be discussed later. Here is an example of a transmitter which is operating at a frequency of 915 megahertz, and the frequency deviation it is into which applied is plus minus 12 kilohertz, and it is required to calculate the maximum and minimum frequencies that occur during modulation, and is very simple. Just by adding 12.5 and subtracting 12.5, we can get the maximum and the minimum deviation in the frequencies of the transmitter. What is frequency shift keying? It is the digital version of frequency modulation, and whenever the information signal is a digital signal and it is applied to the modulator where the carrier signal is also kept into consideration to produce the modulated signal, then the resultant signal will be a frequency shift keying signal. We can see here in the diagram, whenever we have a digital signal represented by 0 and 1 binary version, and that square pulse train signal is being used as an information signal at the input of the modulator where the carrier signal is coming, then the resultant signal will be an FSK signal and is a digital version of the frequency modulation. You can see from here, whenever we have a binary 0 signal applied, the frequency is minimal, and whenever that signal is a binary 1, the frequency is maximum. What is a phase modulation? Whenever our carrier signal is varied in accordance with the information signal in such a way that its phase is being shifted, then this kind of modulation is called phase modulation. Here we have the carrier whose phase is shifted at different degrees whenever we have an amplitude of modulating signal which is varied. Phase modulators are the devices which are used to produce phase modulation and a phase shift in the signal, which is a phase shift is basically a time separation between the two signals of same sine wave frequencies. Here, whenever the amplitude of the modulating signal is increased, the phase shift produced by the phase modulator will also increase, and the maximum deviation produced by the phase modulator occurs when the modulating signal is changing at its most rapid rate, which can be demonstrated in this diagram over here. Here, whenever an information signal is applied at one input of the phase modulator and the carrier signal, which is of high frequency, is applied at the other input terminal, then we are being resulted with this kind of signal, which is the phase modulated signal. And you can see from here, whenever the amplitude of the modulating signal is maximum and where it is minimum and it is changing at its rapid rate over here, you can see the phase shift is maximum over here. One thing to remember over here is that in a frequency modulation signal and in a phase modulation signal, there is no change in the amplitude of the signal, and this should be kept into consideration over here. Let's now discuss about the relationship between a modulating and a carrier deviation. In both the cases, in FM and in PM, the frequency deviation is directly proportional to the amplitude of the modulating signal, while in phase modulated signal, the maximum amount of leading or lagging phase shift occurs at the peak amplitudes of the modulating signal, which can be originated from the previous diagram over here, where we can see when the maximum amplitude and the minimum amplitude in between those two times, there is a maximum phase shift in the phase modulated signal over here. Similarly, in a phase modulated signal, the carrier deviation is proportional to both the modulating frequency and its amplitude, which can be seen from this diagram over here. You can see if we have the y-axis, which is representing the frequency deviation, and x-axis representing the modulating signal amplitude and the frequencies, then we can see that the carrier frequency deviation and the modulating signal amplitude are linearly related with each other for both the frequency modulation and the phase modulation. While the carrier frequency deviation is related to the amplitude of the modulated signal for a phase modulated signal in a linear fashion, while for a frequency modulated signal it is related in a unit step function where it is constant, the frequency deviation, which is defined in anticipation in the frequency modulator, the amount of change of frequency which will happen at the low and the maximum amount of amplitude times of the modulating signal. Now we will see how to convert a phase modulated signal into a frequency modulated signal. Now for that purpose, the frequency variations in the modulated signal must be controlled. As you can see in the previous diagram, where we have on the y-axis the frequency deviation of the carrier signal, which is represented in the y-axis, and the x-axis is representing the modulating signal frequency. You can see that as the frequency of the modulating signal increases, the frequency deviation of the carrier also increases linearly with reference to it for a phase modulated signal. So in order to make it a frequency modulated signal, its frequency must be controlled in such a way that the high frequency components, which are exceeding the behavior of the frequency modulated signal, must be eliminated by some filter, which can be a low pass filter. So once it is being done, then the phase modulated signal gives us the behavior of the frequency modulated signal nearly, and is being said as indirect frequency modulated signal. So how to do that kind of necessary work? We for that purpose need a low pass RC network, which is also said as a frequency correcting network, a pre-distorter, or 1 by F filter. And it causes what? It eliminates the higher modulating frequencies occurring in the modulating information signal. And so once that kind of modulating signal is being given to the modulator, it will produce a kind of indirect frequency modulated signal which is produced from phase modulated signal. We can see that behavior diagrammatically, where we can see the microphone, which is the transducer getting the information modulating signal, is being amplified by the audio modulator, is being given to the RC filter, which is a low pass filter, and it does what? It removes the high frequency components occurring in that modulating signal and is being fed to the phase modulator, from which is also getting a carrier signal and is giving us an indirect FM signal. This diagram is representing the behavior of the filter, where we can see that the filter is attenuating the frequencies beyond this point and is allowing the frequencies beneath this point to pass through it and attenuating the frequencies beyond this point, and this is a representation of a roll off of the attenuation of the RC filter. So what is phase shift keying? Whenever we have a digital signal in the form of pulse train which is applied at the input of the phase modulator, then the resultant signal will be a phase shift keying signal, and it is a kind of digital explanation of a phase modulation. We can also say it as binary phase shift keying, because here we have two phases which are being used, 0 degree to represent a binary 0 and 180 degree to represent a binary 1, and we can also use some other phases to represent various other amplitudes as well. The PSK signal has a constant frequency, but its phase changes with the degrees we are using to represent various binary information. From this diagram we can see the exact behavior of the PSK signal. Here you can see the binary 0 is represented by this phase representation of the signal, and the binary 1 is represented by this phase representation, and you can see when the information is changed from 0 to 1, there is a 180 degree phase shift which is happened at this point. Thank you very much.